So, ScopeIO is a library to debug in a device. That is, you are writing a device in FPGA, USB, whatever you want. And the problem is that this is inside the FPGA. So, if you need to debug something, what they are going to use is an oscilloscope or a logic analyzer. The problem with the oscilloscope is that you have maybe 1 points. The problem with the logic analyzer is you have a lot of points, and then you have to connect to the FPGA. Sometimes it's really complicated. So at the time when I was working on not exactly ScopeIO, but in the device was a modem. Was an MD modem. That is a Wi-Fi, basically. So I wanted to check if one signal that was there was the correlation. That is, you have an ADC that goes here, and you want to see the correlation. So you cannot do that, even if you had to produce the correlation here, and then you had to check in an oscilloscope if you are getting the correlation right. So what I did was taking the correlation here, sending it to this embedded system, and checking in the video. So that was the first time I started. This is an application. This is not exactly what is ScopeIO, but it's what you can convert ScopeIO into an application. This is the ULX3. It has its ADC, and you can see how it works as an oscilloscope. Of course, the ADC is about 1 megahertz sampling rate, and you can see how it works. This is a video. Nothing that is here. I want to emphasize something. There is no CPU here. Okay, because CPU is nice. It's easy to program, but it takes a lot of resources. And then there is a problem of booting, having a software, a firmware. It's a lot of hardware, more than maybe you want to try, also that you have in the FPGA. So nothing that you see here is made by the CPU. Everything is state machines, simple state machines. All the picture that shown before, it was done by a ROM. Now everything that is here is done by a core, a simple core that decodes the binary into decimal. Yeah, there is nothing strange, nothing limit you that what you can use. The controller that you can see there is there are the 4 buttons that is in the ULX3. Yes, those 4 buttons only. And everything that is there is done with a state machine. So it's not complicated, the state machine. Maybe you can see in the next time. So I made this video when I ended that state machine to control with 4 buttons, because if those interfaces are available at the same time, you can control the ScopeIO plugin into the PC also. So the first time here is that as the ADC is 1 megahertz. If you want to have the best sampling rate for one signal, you can only see one signal. What is showing there is the different trigger modes. You can add the trigger mode that you want. So this is the simple one. This is the one that everybody uses in an oscilloscope, because it's a demo that you can download the bit file and plug it into the ULX3 and it will work. So I made it that way, but you can, there is a module, well-defined module, where you got the inputs and there is the output that you trigger. This is the only thing that the waveform need to know. So what you can do there is your wishes. You can take the whole signal, for example, and do some math manipulation and then say, this is what I want to see. What is the second line is a trigger line. The first, that is, let me see. Okay, this is the offset of the trigger, the mode of the trigger, again, and then we can move the signals. And you always have the scale at the left. That is something that most of the oscilloscope doesn't have, so it helps. Also, you have the time channel, and the difference is behind the difference between the oscilloscope and this is that you have 3 segments. One is the continuation of the other, so you can see more signals. More the signal. Okay, this is playing with the scale, and then when I change, let me see when I change it. There. So I select the time scale and I change it. When I change it, that is, now you have less resolution, the second signal appears. And that will happen with all of it. There I am selecting the second trigger, so we're using the second signal. And this is for all the signals, you have the same. Again, it changes the time. There is more. Let's accelerate this. And here you have the maximum number of input that the oscilloscope has. Another thing. If you see there, you have negative times. See? So you can go. You can see what happened before the trigger. And you can see what happened also after the trigger. See? So you have those delays included in the waveform. What you can measure is what you want. That is, this is an analog waveform. You can have a digital waveform that is always simpler because of 2 conditions. One, which you have 1, 0, 1. The second is that most of the time you don't overlap the signals. It's one after the other, so you only need 1 trace. Here you need 8 traces. Yeah. The number of traces is, you don't have to do anything, only to tell how many traces you are going to have. The hardware description language, we will do everything for you. So this is an application. It's an application if I have an IDC here and take this and represent to the video. But the idea of this is that you can have a device inside. You can take all the signals here and you can see it on a video. So the second time I used it was to debug in a DDR controller, because as I was working with this, with the signal that was really high speed, I need a lot of samples. Let's say a lot of sample was 1 mega sample capture, and you really need at least at that time an expensive equipment that can do that. You see how fast they can go, and also how much memory they had say, and you see how fast a DDR. I'm not saying that DDR2, DDR can go. It's like you don't understand why it was so expensive. Why those equipment were so expensive. So I made a simple DDR controller, but for that to happen, you had to debug this, because there are some things about, especially the DDR. The DDR is really annoying because I think I passed DDR. Okay, because when you need to read the data and the clock are aligned, and that is really annoying, because this was an Spartan 3, and Spartan 3 doesn't have any kind of delay that you can well predict to read the data. So I needed this to synchronize the gates and see if I was reading the data right, in the right mode. So what I did was writing a sequence here, a counter, and then the output of that counter go to the ScopeIO, and what I should see is a signal like this, because it was repeating. Well, I found that the signal was doing this. So I realized that I was missing the first. So this is the way the ScopeIO is used. So all the functionality that I am adding now has to do with capture the data and make it a friendly using interface. In that way, no graphics, no GUI, but how you embedded the module inside your design or with your design. There are many things here that has to do with parameter. For example, the video. It's easy to say, okay, connect that to the video. What's the resolution? How fast? How many of these do you want to see? How big is your FPGA that is going? Your FPGA is going to support 3 or to support 1? The most longer is this, the most block RAM is going to use, because you need to capture the data. There is no memory, no graphic memory here. There's no graphic memory here. All the data that is captured or stored is the one that comes from the ADC. So there is no line for video there. The video is generated in real time. There is no buffer. And everything that is all of that parameter had to be passed to the ScopeIO. How much of the past do you want? That is, we see that you have negative time. That means that you store all that samples. How much do you want to see? Because maybe the event is coming in the future, but you want to see what is back. So that's a problem. What is in the future doesn't matter. You leave it and that's it. But sometimes you have the problem with the past, not with the future. So anything has to be configured in the module. So there was a reward since the one where I used that is completely different, but it's more easy to use to make this more friendly. to make the use of the ScopeIO more friendly. Also, the control is independent. From the embedded system, so you can have serial, asynchronous, sorry, USB, Ethernet. All of that can be used. Also, there is a new interface can be added without changing the module. What else is more interesting? Well, there was I invested a lot of time in a core here, the DDR controller. Now the DDR controller can control single data rate, double data rate 2, and double data rate 3. And it is supposed that there is no difference between the DDR3 and DDR4. So to the DDR4 it should work, even there is no, I haven't seen any kit with DDR4. Between the DDR and the DDR2 there is no much problem, but between the DDR2 and the DDR3 there was a lot of different things. But so why do I need a DDR controller or a DRAM controller? Because sometimes you need to get data at high speed. Suppose that you are debugging a serial input and you want to capture this data. If you use a standard system, maybe you get at least you have a 5 gigabits Thunderbolt or something like this. You are not going to dump the data fast, and those are expensive kits. So, for example, here in the ULX3 you have 16 bits. And the maximum speed that with the micro memory you can get is 200 megahertz. So if you multiply this by this, you can see that at least you have 2 gigabits of data to capture. So, for example, if somebody says that it's a kit on for education, suddenly this, if you want to capture one of the serial, I think there is some serialized input, no, in the ULS, no, but if you have the DDR, you have the gear, what lattice called gearbox 2, that is an input that goes at 800 transactions per second. So it's the number of it. You can dump this data into the DRAM and then dump the data through a USB, through Ethernet, or even through a WAR at lowest speed. So this is why it's so important, the DDR controller here. The DDR controller is included in the ScopeIO, and the fees are external because the fees change depending on the FPGA, and the system is meant to be portable to any FPGA, to any family, to any vendor. So this is for standard. When I started, this was a standard Spartan 3. I passed to Virtex 5, passed to the RTX, that is a Virtex 7, then went to the ECP3 and the ECP5. ECP3 is completely different than the ECP5, the outputs. And I ported this to a Quartus, but this is only an abstraction exercise because I don't have any kit for that. So the controller, that is what you mostly you see in the data sheet, because data sheet tells you have to do this state machine, and you have to synchronize with the DD-RAM, with the chip, DD-RAM chip. But it doesn't say anything else. Most of the designs put both along, and then you have the problem that if you want to port to another FPGA, to another device, or to another for another purpose, you can't. There is I see many examples saying, okay, I made a DDR3 controller for that project, and of course I'm curious about and I want to see if I can improve my design, or there is a good idea, and suddenly I see that is the design and the FPGA are monolithic. It's a monolithic design. You cannot port it. It's for that, and also for that application. Cannot be ported to other applications. So this is one of the things that take me most time during those years. And one of the achievements that we did when I was trying TDDI with working with Goran with the M4, he needed to test his DDR3 mounted in the M4, and we made it. That is, I was working in Argentina. I wanted to try this because it's really painful. The DDR3 and the gearbox that in all of the FPGA are really painful to work. All works different. And for example, in the Xilinx has some black boxes that are not documented. They say that they are there, and not documented. And the FPGA can go faster. So instead of using those black boxes, if you use the delay lines, you can make it go faster, double the speed. So I wanted to make it works, and well, we can make it work. And the others, to understand how flexible is, or trying to make it, then we tried the Orange Craft. But the Orange Craft has a different, I don't know, and it turns out that has a delay. That is, the M4 is faster to send you the data, 1 clock faster to send you the data than the Orange Craft. So if you use a core that was designed for the Orange Craft, probably it won't work in a 40M. But as I was trying to always doing this core flexible, because I want the ScopeIO can be done, can be used in any FPGAs, because I think that the FPGA should be seen as a commodity. That is, today maybe Lattice, but is suddenly Xilinx offer me a better offer. I don't want Lattice because Lattice is increasing me the price. I want to go to the cheapest one that fulfill my expectation or my specification. So we are talking about a new GateMate. Okay, I want that this work on GateMate too, because if GateMate is cheaper, I want to go to that, and it works with my specification. Why I should pay for Lattice or Xilinx? So this was all what I always had in mind, and with this design, it was easily to turn those latencies, because if not, the FPGA was the same. So why, if I use another DDR RAM outside, I have a latency, 1 cycle latency more. So I don't know how it was routing one or how it's routing the other one. I don't know what happened. But what I need is this. What I could do is, okay, I could tune. The problem was the fee. I could tune the fee so I can capture the data without any problem. So ScopeIO. Also, I want to end with a conclusion. ScopeIO is a tool for debugging your device inside the FPGA. You can simulate the whole device. I always simulate the device, but when there is what's called a glitch, which is really hard to get in a simulation. If you don't know what is happening, you cannot go to the simulator to find what the problem is. So what I need was repeating the signal. They say, I think the problem is this. One of the other problem besides this was a refresh system. You have to use a refresh system. A refresh system is it's really a problem because you have to stop depending on how you want what you are doing or how you want or what you want to do. For example, you are doing a video card, you don't have any problem. You don't have to refresh the system will be refreshed by itself. But if, for example, you are doing this, that is capturing data, you are not doing always the DRAM. You are writing from time to time. So what you need is a refresh system. The refresh system will interrupt you in any moment, and then you have to resume where you were to go on. And I have a glitch. I didn't know what it was, and was only when I used the ScopeIO with the output that I saw that there was a glitch in this one side and a glitch in another side, and then realized that was the time of the refresh system. So then I went to the simulator, and then I could find the bug. So this again, there is a system for debugging. This is an application. It's a really nice application. You add in the bit file in any car. In any kit, you say, okay, you have something useful from the start. It's not something that you're gonna see there. No, it's something useful that you can use. But the main goal of the ScopeIO is debugging the device that you are using. So this is, I don't know if it's okay.
Yes. Thanks.
I
think there are questions for sure.
Yeah.
Yes.
So, and what are the, like that ScopeIO, that's like some soft part inside the FPGA. What are the how much resources it needs?
About 4K loops.
Okay.
So
for loot on a for loot device
yes, on a for loot device is
it will be less on your Artixis.
Yeah.
And you wanted to ask how we did the synchronization, so maybe you can shortly explain. Okay, but now I'm curious because it wasn't maybe perfectly clear from the presentation that these limitations of the sampler rate were not inherent to the ScopeIO but to the chip. The cheapest possible ADC that we could find when we decided on what to build into the ULX3 board. So this is one side of the spectrum, as slow as it gets. What's the other side of the spectrum? How fast were your sample rates when you debugged the worst things that you were
I was using to debug. I was using as fast as the DRAM, so I can capture this 8 mega. This is the fastest I can go. Is here are the pins. So here, if I have 400 megahertz for this device, I can capture. I don't have any problem with this. This goes to a FIFO that runs as your highest speed. So if the DRAM is fast enough, you can dump everything in the DRAM.
And from DRAM it goes to the DDR or SDRAM or something?
No, that is the in Xilinx this can be done at 500 of I think 500 megahertz is that you can go, and DRAM 3 in the with the core in the Xilinx 3 in the RTX 35, I make it go at 1 giga transaction per second. So this how fast as you can done in the RAM.
But my question was, could the ScopeIO also sample and not how fast can it dump the data, but it can sample at really at 500 or what, even can it sample at double data rate?
Yes.
So
I can.
You could do 1 giga samples per pin per digital pin.
Yes.
Of course not.
Yes. Yeah, because it depends on the. So the only thing I had to cut is sending it the data. That is, I capture this and send to the ScopeIO to a FIFO, to the block RAM. That is how fast a block RAM can go. And this is your limitation. I am not doing anything with the samples before. I capture as they are, and once they are captured, they are sending to the system. The system works at video speed.
And how fast did you get the DDR3 on the ULX3S and the Orange Crab?
In the same as you, it's the 400 megahertz. You cannot go faster.
Yeah, and the 400 megahertz is actually when you buy a core from Lattice. That's the maximum you get if you buy the fastest speed grade of the FPGA. But we had speed grade 6.
Yes, you can see in the other way, that is the RT kits that Xilinx sells can go at 300 megahertz. This can go up to 500 megahertz. I tested it. So there is nothing new. The only there are some other cores that made something similar, but the difference with the other cores that you don't have to tune this, that if you don't have to game any constraints, it will do it for you. And it is automatically. You ask for the maximum speed, and the core will do it. The idea is that also you don't remember what I said about I want something that a friendly user interface. So I'm working on that so that if you add the DDR3, you add the speed that you want to go, and all the other parameters are set by itself. You don't need to add any constraints, only the pins.
Okay, I have maybe one question. You tried two boards, ULX3S, Orange Crab. Both of them has similar ECP5, DDR3, but you mentioned there are some differences. Are in your library these differences, how can I say, automatically integrated?
Yeah, no, you cannot automatically integrate, but you can describe it. So I described it.
Okay.
So if you want to use the Orange Crab, you have you pass the feed that is an Orange Crab, and it will delay the data. Yeah, sorry. Yes, it will delay the data. Well, delay the data and saying I have the data here. If I have to use the 4M, you use the description for the feed for the 4M, and it will send the data immediately.
What's your explanation? Why is it so? Because it's the same chip, same DDR. Is it different pins that are?
I don't know.
Yeah,
Okay.
the pins,
I
because
don't
the
know.
only difference is like when I have connected it, I didn't use I don't know the pin now how it's called, but I did switch. I think it is selecting something. So two pins are switched on my board. It is originally done good on the orange crab, but I did some problem. I connected the pins like opposite, so I connected. I don't know. Maybe I don't know how.
Okay,
Not all pins can go to the four times gearing. Is that the problem?
No. Everything that needs to be, because Lattice has like DDR3 part inside, so you need to connect most of the pin to the exact pins. So, but there are two pins that you can switch. So you can switch them, and we will find a way how to use them. So Lattice is not complaining, but maybe that is the thing. But that's the only thing that is different in the hardware, and also like routing and that.
So this is really a big topic, so maybe we can expand it tomorrow or but just as a hint. So you said that the biggest problem with all DDRs are in device and in delaying data, and you're trying to make it as generic as possible and to decouple the real digital core from this 5 front end. And one obvious thing that the 5 front end must do is delay data and even probably fine-tune the delay at runtime.
No, because
how you delay
that is,
data?
for us, maybe we enjoy playing with the delays. But think for somebody that is a user, they don't want to play with the delays. They want to capture the data. They want to make knowing anything about the DRAM. They would say this is useless. So what I could find is that okay, I can have the feed here and the core, the DDR core that is isolated. So when you are in ScopeIO integrate the DDR core, and this is completely portable. It is only sequence. That is, when this DDR core had to do this, that is read leveling or write leveling. That's the name. The DDR core as the feed do the read leveling, and the feed start doing the read leveling. The read leveling is the alignment that we see before. That is the read leveling. And then the feed ends. With that read leveling, I don't know why, with the orange cap, and we tested two different ones, one from Goran, and there was another user in Discord that tested his own, and in both works with the same delay data. So it's something something particular, I would say, in the 4M that is in some way suitable because it's faster. It gives you the data faster. You don't have a delay, an extra cycle.
So you want to say that 4M
is
faster and 4M
more real time.
Because I made a mistake.
is using no standard way of connection, but it was better
why.
choice.
I don't know why.
Maybe Goran knows why.
I don't know why. But that is what is happening.
My biggest question is how you what are the tricks done in the PHY, which obviously you have to devise using whichever components you have, device specific components you have at your disposal.
Yes.
Are you using digital delay lines? Are you using PLL and variable tune the delay in PLL, or mix the both approaches? How is this done?
No, in the case of the ECP5, you have to follow what it is in the datasheet. And also, there is a small device that only divides the frequency by 2 over 3.5, and you have to start it well. And there is a core that hopefully, luckily it was open. That is the best way to start this. I don't know exactly what it does. It's written in Verilog. I don't care. It works. So I am using this from Lattice, and that module started that device, that part of the device well. So I try to, in the case of the ECP5 for the DDR3, I tried to use my method. It didn't work. So they say that you have to go step by step and waiting a little bit of time till the system synchronizes, and it will tell you when it is synchronized. So there is no delay. It's always managed by those basic logic blocks. So they explain very well how those logic blocks works, but there are some darks things that you had to try. This is, well, I remember when we started trying and was sending him I have another bag there, but it was mine bag, it was here. I was sending the bit files to Goran, and Goran tell me, no, it doesn't work. And I asked him for a dump, because when you test it, it gives it a dump. And there was always a delay of 16-bit. So it was written well, but it was written wrong. And what I had to do was compiling the VHDL system, doing with the whole delay, that takes a lot when you're using model sim to simulate it, takes a lot of time, and I could see the problem. But it's not something that I was doing wrong, it's something that how this thing starts up, how this counter starts up, this divider startups. Because if it starts wrong, it won't work. And you have this code written in VHDL that was, because it's in the datasheet said, oh, you have this core, and suddenly one of them start to check this is a soft core. So it's not something that is a black box. It was written by Dennis, and luckily I could find where it was, and I added to the project, and it works. So it's not something that the latest documentation is very good, but it's not as good as the Xilinx. Xilinx has a very, very good documentation. This is why maybe we are leaning. I am leaning to go to Xilinx. Sadly, the DDR3 black boxes are not documented. They tell, use our system, visual system. I didn't went there, but the documentation is really good with all the applications. Lattice has also a very, very good documentation, but there are dark things. There are really dark things. And the starting up of this divider, they say, no, you have to do this. No, you have to delays. You have some latency between the startup of some of the block here and the divider. If you don't do it, it won't start well. So there was a lot of time invested in doing this and this, because also one of the problems that we had with Goran when I was sending the test is that Goran suddenly tell me it's stopped. It didn't dump any more data. Yes, and yes, there was a problem. It was my problem that I couldn't found it, and I found it by chance when I was adding some module into ScopeIO. Because even in simulation, I tried in simulation to say why is, and I couldn't find it. So it was really a glitch. I couldn't reproduce that glitch. And so I could find it, and I tested everything, and it works.
And this simulation, how does it effectively last on a normal laptop computer?
The functional simulation or the because there are two things. One is the functional simulation. When I see a glitch, I do a functional simulation. I don't know a low-level simulation.
Mm-hmm.
I did a level simulation with the DDR3 with Goran, and I did that kind of simulation. I found something with Xilinx that's very interesting. I did that kind of simulation when the function simulation doesn't match with what I see in the real life, and it takes a lot of time.
What in one run of the simulation? What is it? 5 hours or something?
No, you have to, depending where it is. Maybe it takes half hour, 1 hour. It takes time because it's simulating all the delays inside the FPGA. So it's but you go there when you have something like this. I don't go there most of the time. I use simulation. If I don't, for example, the USB device that is in ScopeIO, first it was pure simulation because I didn't know that it's with the bit stuffing system and how you have to correct it. I was sure that if I didn't simulate it first, it won't work. I would have lost a lot of time.
Maybe I can answer your question, because today as an exercise I was playing with a FIFO and simulating 1 millisecond of some crazy logic that I was playing with at 1 megahertz simulated clock. So one simulated millisecond of FIFO system with a bit on the right side and the read side took about 1 minute to simulate, just to get to a waveform, and this was the footprint of this was less than 700 loops. So if you go, yours is 10 times bigger maybe when you embed it in, and it's a lot more complex. So, and this is on a machine that doesn't have all the antivirus software which corporate headquarters have thrown at us. And if you run it on a laptop, then it's like 13 times slower. So it's not ridiculously slow, but you have to know what you're looking for, and you cannot start from a random point. You have to prepare the simulation with an exact.
What you're looking for?
Yeah. Otherwise, you are lost.
Yeah, this is what I wanted to. How? Yeah, that's the answers. Yeah.
Okay, then tomorrow we can check like code and how everything works and maybe explain more, but thank you.
Oh.